Okay, we can start our afternoon session with Andrea Mari. So the title is Can AI Learn the Best Way to Use a Noisy Quantum Computer? So here's the microphone.
Okay. Yeah, so first, thanks for organizing this very nice workshop and for staying here. And yeah, so I am not an expert in quantum machine learning. That's not my main research field. And when you have to give a talk on something where you are not an expert, you start with a question. And so I also don't know the answer to this question, but I will give some evidence, some results and some ideas that go in this direction, okay? In particular, I will focus on three aspects in which I have some results to present. And then I will spend some time with this last open question, which is just give a quantum computer to some kind of artificial intelligence and let the artificial intelligence decide what to do with the quantum computer, okay? But let's go slowly from the human-driven towards the direction of AI-driven usage of a quantum computer. Let's start with the concept of dressed quantum circuits. So this is a bit old results. It's related to already at 2020, we started to try mixing classical layers and quantum layers together. But before I go to the definition of a dressed quantum circuit, let's just review very quickly what is a classical neural network. Here, I'm sure you know very well what a classical neural network is, but just to set the notation, we have a sequence of classical linear layers followed by local nonlinear operations. But if you see the full neural network as a black box, it's just a parameterized function from x to y that depends on some trainable parameters theta, okay? And again, a quantum neural network can be built using variational quantum circuits. That's an option. And usually you encode some classical data on the variational gates of this circuit. You also have some trainable weights, and you get prediction as, for example, expectation values. This is not the most general variational circuit. You can mix the input data all along the circuit. You can have a lot of different structures. But what is important is, again, if you see as a black box, a quantum neural network is a parameterized function from x to y that depends on some parameters. And of course, the hope is that this function is a bit difficult to compute classically. It's a different, you have access to a different ansatz of functions, hopefully. And so maybe a quantum computer can be useful also in this setting. However, typically, if you have a variational quantum circuit and you have a fixed number of qubits, you don't have a lot of freedom in the input and in the output. For example, if you have 10 qubits, let's say, no, let's increase these numbers. Sorry. If you have 100 qubits, 1000 qubits, but still you want to embed into the circuit an image, usually you have a lot of problems because the input classical data that you want to embed into the circuits, it's much larger than the size of the circuit. And to avoid this kind of problems, we introduced this very simple model, which is just a sandwich of a quantum network with a classical layer before and after it, okay? We called it the dressed quantum circuit model. And what is the advantage of this model is that you have complete flexibility in the number of inputs and outputs. But the aspect that I want to stress here in this talk, which is related to the initial question, is that you can also give a physical interpretation of this model as a architecture in which the classical layers that you have in the input and in the output somehow learn how to use a quantum computer. Because if you train the full model together, the classical layer at the input somehow learns the optimal way to encode and to embed information into the quantum circuit. And the classical layer at the output learns how to extract and to post-process the information from the quantum circuit. So this is a small example in which you are automatically learning how to use the quantum computer. It's a first step in this direction. And yeah, very recently, you may wonder how it works, how it performs this model. It was done a systematic analysis of many different quantum classifiers that have been proposed in the literature. And this DREST quantum circuit was performing quite well. Here in this rank, good is up and bad is lower. However, I have to say that, as you can see, there is this rectangle in gray, and that's a classical machine learning model. So fully classical dense network is better than all the models that have been proposed in the literature up to 2024. Of course, for this particular data set, it was generated completely synthetic, and it was just an attempt to systematically measure the performance of some models. But this gives the idea that maybe it's not so wrong to mix classical layers and quantum layers. Okay, if a single layer placed before and after a quantum variational circuit helps, what about using a very deep classical network before or after a quantum circuit? And that's something also that we studied. And for example, in this example, we used a DREST quantum circuit, which is the object that I've shown you before. But before going into this, we used a state-of-the-art deep neural network. It was state-of-the-art a few years ago, but now it's an old model. ResNet 18 is a very old model, but still millions, maybe billions, I don't know, a lot of parameters, classical parameters, together with a quantum circuit. And this was the only way to basically process high-resolution images with a quantum computer. And okay, this was just a proof of concept demonstration. We don't claim any advantage, of course, but it was just to give the idea that maybe taking the best, even in the previous talk, I think by Macaluso, there was this idea of taking the state of the art of classical and changing a little bit with some quantum, and maybe you get something. But of course, what is the big problem of this setup is training. If you have billions of parameters and you want to train all together this object, is a very crazy idea. And so the only reasonable way of doing this is transfer learning. And so we try to generalize the concept of classical transfer learning into the hybrid classical quantum domain. And so first, what is transfer learning in general? It's the idea of training a network or a model on some generic data set for some generic task, and then using the same pre-trained model for a new specific data set and a new specific task by only training the last part of the model. So you remove the last layer or a couple of layers, and you train only a small part of the big model. And why you do this? Because it's much easier. So you can invest a lot of computation and time on creating the generic model, and you can train with much less time for a new specific problem. And so using this approach, basically, we could just take the big pre-trained model from Microsoft, in this case, the ResNet 18 model, remove the final layer and replace it with a quantum model. Of course, 4 qubits, it's ridiculous. But again, this is just a proof of concept of the idea of transfer learning in hybrid classical and quantum systems. And this was just a proof that you can at least process high resolution images, and so a lot of classical data when you have a small quantum computer. Well, this, I don't know, it's, I don't remember, but it's not so important, the actual resolution, because anyway, you can do downsampling to adapt the network to the image. I think, of course, to recognize the animal here, you don't care about the high resolution or not, but it's the fact that it's an image, it's already a limiting factor. It's impossible to encode an image in current state-of-the-art quantum computers without a pre-processing part. That's the main message, unless it's a very simple image.
Here is the classical layer that we trained.
The L is a classical layer. Okay.
So what? Because you have like a code or
It was like a rotation encoding. 4 qubits, each qubit is rotated with a sigma y rotation. And yeah, but don't take seriously this, this circuit, okay? It's 4 qubit. Of course, if you replace the 4 qubit quantum computer with a classical layer, you do more or less the same as performance. But that's just to present the idea of nobody knows what happens for a different input. Maybe images are not so interesting, but with 1000 qubits, things start to be more interesting. Yes.
So in example, the model are training is trained in sync after and then the fine tuning already in sync translation and also.
In this example, with this image that you see there, yes, but then we also changed the images. We took another data set and it also works. Yes, also different data set. Okay. This was a first attempt to let classical machine learning use a quantum computer. A second attempt is related to noise. So you can try to mitigate noise with different methods. And an approach to mitigate noise is to use machine learning. So to learn the best way of reducing noise in a quantum computer. And so I would like to say something about variational quantum error mitigation, but also the next point, synergy between classical and deep learning, could be seen as a way of mitigating noise. First, what is error mitigation? Most of you know, but just to clarify the term, error mitigation is something that tries to emulate error correction, but fails, so it doesn't work. In the sense that standard error correction is scalable. It's based on encoding logical information into many physical qubits, measuring syndromes, and correcting errors in real time. If you are not able to apply error correction, and we know that it's very hard, error mitigation is a very simple alternative in which you simply run multiple and different noisy quantum computations. You collect all the results, and you infer ideal expectation values from post-processing noisy data. So there is no real-time feedback into the circuit as in error correction. This is, by construction, asymptotically unscalable, but it's very easy, and it can be a practical solution in the near term. Questions about this? Okay. what is the workflow of most error mitigation techniques? The typical workflow is something like this. You have a quantum circuit as an input. From this circuit, you generate several auxiliary circuits. And I will give some examples. They depend on the input circuit, but they are different. They can be different, and they can be like mutations of the input circuit. You execute all these auxiliary circuits, you compute results, typically expectation values, and you combine the measurement results to infer what will be the ideal expectation value evaluated with the input circuit with an ideal backend without noise, okay? What is important is that you generate different circuits and then you do post-processing, okay, without any real-time error correction. What is the hope is that if the direct execution of the input circuit with your noisy backend gives you a biased estimator, if you do these tricks, you get a less biased estimator, maybe even unbiased, at the cost of increasing the variance. And so error mitigation has a sampling cost, but at least it can reduce the bias of your estimation. This is a nice review of all existing many of the existing error mitigation schemes. Okay, just to give you an example, a very simple but still quite effective way of mitigating noise is zero noise extrapolation. In this method, you take a circuit and you run different circuits with different level of noise. Usually you increase the noise, okay? It is given as an assumption that you cannot decrease the noise. Of course, you have your noisy device and that's it, but you can increase the noise. And I will give you an example of how you can increase the noise. And of course, if you have some expectation values at different levels of noise, you can try to extrapolate the zero noise limit. It's just a fit of a function with some models. That's the idea of zero noise extrapolation. And a small advertisement, if you're interested, Meetic is an open source library for doing this kind of error mitigation tricks with most of current SDKs for quantum computing. Okay. But how do you increase the noise for zero noise extrapolation? Well, there are several ways of doing it, but let me just focus on one of them just to give an idea. Let's take global folding. It's a method in which you take a circuit and you append to the circuit the inverse and the circuit again. And maybe you do this several times. Each time you do this, if you run this on a noiseless quantum computer, that's equivalent to this one, because G dagger G is the identity. But if you have noise, you increase the noise, in this case, by a factor of 3, for example, more or less. If you do this, and you run the same circuit with different level of noise scale factors, you can try to do zero noise extrapolation. But and later we will use this information, this fact of mutating the circuit in this way. But let me just focus on this aspect. Most of the error mitigation methods, including zero noise extrapolation, depends on some parameters, okay? We can call it hyperparameters if you want, if in the language of machine learning. And so you have to tune those parameters. For example, what is the optimal number of repetitions of this G dagger inverse G dagger inverse G? What is the best model to fit the extrapolation in zero noise extrapolation? But also many other methods are parametric, like in dynamical decoupling, you have to choose the gate sequence. You have to choose the scheduling time when you apply the gates in a circuit. So you have a lot of parameters that can influence the noise of your computation. And so the idea is, what about if we try to tune error mitigation parameters in the same way in which we typically tune gate parameters in variational quantum circuits? And that's the idea of variational quantum error mitigation. Okay, what is there a pointer? Okay, yeah. Yes, okay. What is the typical loop of a variational quantum circuit? You have a problem like minimizing the energy. You set some angles, you do measurements, you compute the energy, you optimize the angles and so on. And the idea is, let's put also the parameters of error mitigation in the loop. If your task is minimizing the energy of a Hamiltonian, if you get error mitigation parameters that gives you that give you better results, you are essentially improving the error mitigation technique. Okay, that's very simple concept. We try to do this in this paper in which we applied different dynamical decoupling sequences in the middle of circuits. And also we optimized the position of gates that are not fixed by the topology of the circuit. Sometimes if you have a circuit with 2-qubit gates and single-qubit gates, you can move in time some of the gates without changing the structure of the circuit. And so there are optimal positions in terms of noise. And so you can also treat these parameters as variational parameters, and you can put them in the optimization loop. And it gives some advantage into standard kind of benchmarking data sets. But again, the results, in my opinion, are not too important because the systems are still quite small. What is important is the idea of automatically optimizing error mitigation. By the way, a very nice way of using learning methods for error mitigation was proposed in this work in 2021, in which, for example, they trained the extrapolation function of zero noise extrapolation with near Clifford approximation of the circuit that you want to compute. Okay, you can train a model to do the zero noise extrapolation with near Clifford approximation of your input circuit that you're able to classically simulate, and then use the model on the real quantum circuit. Okay. Let's go to the next point, which is similar to the variational quantum error mitigation, but in the previous examples, the classical computational power that we were using was negligible, okay? For example, in zero noise extrapolation, you evaluate the circuit at different levels of noise, and then you just do a linear fit or maybe an exponential fit. The post-processing is very simple and trivial, okay? What about if we use the maximum power of classical machine learning and we mix it with quantum data, okay? To, again, try to reduce the error in quantum computations. Okay, let me just make a very simple example of a standard supervised learning setting in which you have some training data, which is a set of expectation values, EJ, for some observable OJ, that are computed after the application of quantum circuits UJ. Okay, for these quantum circuits UJ, you know the ideal expectation values. For example, just to make an example, imagine that the training circuits are Clifford circuits. You know how to simulate, and so you can easily build a training data set of computations for which you know the ideal results. And then you run the circuits on a quantum computer and you try to optimize your, if you want, error mitigation model. And the test set is again a different set of circuits that you are not able to classically simulate, for which again you want to estimate some expectation values. And Of course, we have a lot of strategies to estimate those expectation values. A possible strategy is to use a fully classical deep learning approach. Of course, you can also use a fully classical state vector simulation, but we know that it's very expensive computationally. An approach that has been proposed in the literature is to simply treat this as a machine learning problem and train a neural network to estimate expectation values given the description of the circuit. Okay, for example, if the circuit is variational, you can give the angles to the quantum machine learning model, and you can try to still estimate expectation value. Basically, you are using a neural network as a simulation method of your circuits. And the opposite approach is to throw away all the training data and just run your quantum circuit on your noisy device, and you get some noisy data. Or maybe you can try to apply error mitigation to your quantum computer. And again, you are using the full power of the quantum computer with a little bit of classical post-processing. Okay? In particular, you can use learning-based error mitigation. As I said to you before, there are several papers from the Patrick Cole group, but also very recently, IBM proposed a machine learning approach to quantum error mitigation in which you do something like this. But again, the inference model is very simple. You don't use a classical network with a lot of parameters, with a lot of classical computational power. So what is the direction that I try to propose is a direction in which you use the full power of classical machine learning combined with the full power of a quantum computer. And the idea is, I will go to the details, but is to mix a classical deep neural network, which can have some access to quantum expectation values that are noisy. And so put in this way, the problem is can be seen as an error mitigation method, but also just as an inference method. You want to estimate the expectation value of some observables, and you're free to do whatever you want to get the good result. Okay, in this paper, which is together with Simone Cantori, who is here, if you're interested on the details, you can ask him, and also together with David Vitali and Sebastiano Pilati, we try to use, to empirically test this synergy between classical deep learning and noisy quantum computer. Okay, assume that you have an ideal quantum circuit with this kind of structure, which is very typical in many quantum experiments. Single qubit rotations combined with ZZ gates coupling different qubits, okay? And many layers of this structure, okay? What's the trivial way of computing expectation values in this case? Assume that the expectation value that we are interested in is the average magnetization of the circuit, which means the expectation value of sigma z for all the qubits, the sum of all the expectation values. What's the trivial way is to embed the circuit into a real quantum chip, like this IBM chip that you see there. You transpile, you measure the observable, and you sum the magnetization along the z direction of all the qubits, and you get your expectation value without any error mitigation and without any error reduction. The opposite approach, the fully machine learning approach, will be to embed the angles of this ideal quantum circuit, so the description of the circuit, into a quantum machine learning model and predict the expectation value. And of course, you have to train the model on similar circuits on which you know how to compute expectation values, but in principle, it can be done. What is an approach that combines the two methods is to, again, give to the network all the information that you have, like the angles of the circuit, the qubits in which you are embedding the circuit into the chip. Okay, you have a vector of angles, a vector of one-hot encoding of the qubit used in the circuit, plus the output of the noisy quantum computer. You give everything to the network and ask, please give me the ideal expectation value of your observable. Okay, questions about this? Okay, this is the prediction error with this approach. And first, let me focus on the green and the orange line. So what is the green line? This is the prediction error that you can achieve with a noisy quantum computer without any machine learning at all. And you get some plot. Of course, here in the x-axis, there is the noise of the quantum computer that we parameterize from 0 to 1, where 1 is the actual noise of the hardware. Since this is a simulation, we are able to reduce the noise to 0. And of course, when you reduce the noise, you get a better prediction of the expectation value. The other approach is to use a fully classical deep learning approach without using a quantum computer at all. Yeah, because it's not like a mean squared error. It's a ratio of variances, and it can be larger than 1. So the coefficient of determination, I think, can be negative, right? Yeah. Okay, Simone knows. There are cases, of course, when you are in this regime, it's even worse. So the error is, the model is not working. The model is working where 1 minus that quantity goes to 0. Yeah, it's just a technical way of measuring the error, but I think we could have used a different metric. The concept is very similar, so you can come back to this. Okay, so what we see here is that if you have a very noisy quantum computer, you are here, the best strategy is to use a classical simulation method based on a fully classical neural network. If you are here, the best strategy is to use your quantum computer instead of the neural network. But what we have shown is that if you mix the noisy data with the classical neural network, with the architecture that I've shown you before, you can always get a much better result. So you get some kind of synergy between noisy data and classical machine learning. Yeah, that's true. Exactly. Exactly. This is the noise. Sorry, that's a good point. The noise of the control nodes, which is the dominant noise in current quantum of control nodes, 2-qubit gates. We leave all the other like measurements, noise. By the way, we use these fake devices that you have in Qiskit, which is a classical model of the noise, and we just reduce the control node.
The learning plus the quantum computer, so like probability of noise being done. How is that better than the fully classical deep learning, which would just be like uniformly random?
Because one is not fully noisy, it's the state-of-the-art noise of an IBM quantum computer. So we take okay these fake devices that they have to simulate.
This is like scaling
Exactly. When you have one, it's hardware noise, current hardware noise. When you reduce it, you have ideal computers that we currently don't have. Okay. Other questions? Okay. So another specific applications of this approach is in particular on the variational quantum eigensolver. So we know that variational quantum eigensolvers are in principle promising near-term algorithms. Unfortunately, they give interesting results only if the circuits are deep, but if the circuits are deep, you have noise. And so it's very important to try to mitigate noise in this kind of variational algorithms. And what we try to do is to first take the variational quantum algorithm without any error mitigation and show and put us in a regime in which it doesn't work. And it's very easy. If you want to find a regime in which the VQE doesn't work, it's easy because you just take a deep ansatz, which is what you need in practice to have interesting results. And if you try with state-of-the-art noise models, it doesn't work, okay? And then we try to use a different approach, which is first split the circuit in two halves. That's the same trick that has been used by Google to simulate random circuits, but in this case, it's not a random circuit. And you use these patch circuits to run the VQE. You are not using the full power of the ansatz because you are cutting the circuit. That's fully classical. You remove 2-qubit gates such that you have two independent circuits. Okay. Exactly. So it's a very strong approximation. But at least, even with this very strong approximation, typically you do better than a noisy quantum computation because that's classically exact. Okay, we assume that we are able to simulate half of the circuit. Okay. And then you reach an optimal solution, which is again not optimal because we are cutting the circuit. And now you start using the machine learning mixed with the quantum computing approach. So you start training your machine learning model that we have seen before with partially cut circuits that you can again classically simulate if you add just a few control nodes to connect the two. That's called circuit knitting. There is a way to combine two independent circuits if the number of coupling gates is small. That's the circuit knitting approach. So we can simulate classically those computers, those circuits, and you can also run them on hardware to train the machine learning model. And finally, you can just use the trained machine learning models to complete the VQA by feeding the machine learning model with all this information, description of the circuit, and noisy expectation values. And yeah, these are the results. This is like the noisy, where it is. This is the noisy VQE. By the way, we use this very simple Hamiltonian with random ZZ couplings. And the task of the VQE is finding the ground state of this. And that's the noisy VQE, very bad. And this is the patch circuit classical approximation, much better. But what is interesting is this part, which is the machine learning approach, in which we are able to go down very close to the ideal VQE, and so to the ideal ground state, okay, by using a combination of deep learning and noisy quantum computers. Okay.
Sorry, I didn't get how is that working. So what do you optimize in the green part?
Yes. So we do something like this. For example, we are here. We are here to the last point of the classical patch circuit approximation. So we have all the variational angles close to an optimal solution. It's not optimal. And then from this circuit, we generate a set of training circuits with parameters close to this and with the constraint that we still are able to simulate those circuits. Okay, so we generate with this partial circuit knitting approach quantum circuits that resemble the circuits that we are interested in, but we are able to classically simulate. And we use them, we also run them on hardware to train the machine learning model. To train what's the task of the model to predict the expectation values, okay? And then we use the model to do the VQA. So now we have a big black box that contains classical machine learning and quantum computer that is able to give good predictions of expectation values. We can use the big black box to run the VQA. No. Because the model takes as input also the noisy quantum data. That's no. The final step of the blue point is completely classical. So the blue optimization is completely classical because I'm able to simulate it. So why using a quantum computer? But to improve on top of it, you need a quantum computer. Okay. Good. Questions on this part? Because the next is completely crazy open questions. So, okay, let's go to the completely crazy open question. Okay, what about pushing this approach to the limit and just ask artificial intelligence to use the noisy quantum computer in the best possible way to estimate, for example, expectation values or results of experiments. Okay, what I've shown you before, it was an example in which each time you use the model to predict an expectation value, you run a single circuit on your noisy device. But we know from error mitigation that maybe this is not the optimal approach, because in error mitigation, you run a lot of different circuits and you do post-processing, okay? So maybe the following is the most general approach that you can think about, and maybe later we try to make it more implementable. But let's consider this. You have an input circuit, which can be described by the gates, unobservable, and a budget of n shots that you can use on a noisy quantum computer, okay? Imagine credits on some quantum computer vendor, but with a finite number of shots, okay? And the quantum computer is noisy. So question, given the description of U and O and given N, do whatever you want to estimate the ideal expectation value. Okay, this question contains, as a particular example, everything that I've discussed before. Contains error mitigation, it contains synergy between deep learning and noisy results. And the question is, how do you do this kind of approach? Okay, the first solution is just wait until we have artificial intelligence that is much better than us, and they will figure it out how to do it. But if you want to do something now, maybe we should give some hints to the artificial intelligence part about what kind of circuits you have to run, okay? For example, you can say, look, maybe inspired by error mitigation, you have to run the circuit and the circuit concatenated with the inverse many times to understand a little bit the noise model. And from this, you can post-process, okay? And so you can say, let's distribute the budget of n shots to a fixed set of circuits, hard-coded by us, by humans. But after you decide the circuits, all the rest becomes trainable and you can optimize. Okay. But finally, actually, maybe the best approach will be to even optimize the kind of circuits that you should run on the quantum computer. So it's not clear that the optimal choice is to run U dagger U, or U dagger U many times. For example, in probabilistic error cancellation, we know that it's very useful to run the target circuit with some Pauli errors in the middle of the circuit. There are a lot of different approaches inspired by machine learning, by error mitigation. And so the question is, can artificial intelligence automatically decide and learn what is the optimal way of modifying your target circuit in such a way that you get a better estimate of expectation value using a noisy quantum computer? And since I think I finished my time, I skip this. And maybe, yes. And I leave this conclusion slide just to summarize what we have done. So we have seen several results going into the direction of letting machine learning understand how to use a noisy quantum computer, and some crazy ideas for what we could do in the future in this direction. Okay, thank you very much.
Time for a question from the audience. Okay, maybe just a quick one, because
Yes.
in the approach where you combine neural networks and the architecture of the neural network or the classical neural network is something you can decide, right?
Yes.
But somehow you are not forcing anything about the fact that is an input and output from a quantum computer, so it's not informed somehow that we are extrapolating from the data set you have. So can you go just a bit below what you have? It's like an extrapolation of something, right? So you're not ever going to need somehow the value that you find is above the.
Okay, I think yes, that's the variational. In the variational case.
But no.
Here. Okay, yes. Okay, this is a very important question. If you are training an error mitigation model that is like cheating, and so it's just giving small numbers as outputs, maybe you minimize the energy because of this. And so in this work, we used error mitigation techniques that cannot be biased towards lower energy results. For example, we optimized dynamical decoupling sequences, and they cannot cheat because you always create a valid quantum state. And so any quantum state has an energy above.
Yes, but then the second approach.
In the second approach, yes. I agree. And indeed, yes. Yes, but okay, in this case, the training is not done with a loss function that tries to minimize the energy. So the training of the model is done to approximate expectation values. And then you use the model for doing the VQE without further training the minimization of the energy. So the hope is that your model is unbiased. Of course, it could be biased towards lower energies. In that case, I think you should check, at least for this size, you can check if the angles that you find are better than the initial point. But you may have this problem, yes.
Last thing, you said the run the machine then you run it n time. You didn't constrain the number of times you run the circuit previously, right? Like when you're doing the variational, when you're doing the zero error noise mitigation, you just run it as many times as you need to do the zero error noise mitigation.
Yes. So, well, no, actually, typically you, even in zero noise extrapolation or in many error mitigation techniques, you always have a finite budget. And typically, the more the technique is unbiased, and the more is the number of shots that you need. Okay. And so often the number of shots is a very important resource to consider. Okay. In zero noise extrapolation, the main error often is the bias. And so even if you put this n to infinity, you still have a residual error. But in many times, in many other methods, like probabilistic error cancellation, you have a less biased estimator, maybe even unbiased, and the number of shots is very critical. Okay.
Yeah, well, thank goodness. Thank you.
Thank-